All right. Good morning, everyone. Let's get started. First of all, let me just clarify on 2 points about last session. So we normally use the available data from all the INJs for like x1 and y1 up to xn yn in order to predict for our specific, for instance, in a case of recommender system, for the specific INJs that were not in our data set. So we use all the data for all the movies ratings and also the other users rating for the specific user that wants to predict. Not only that user's data, but the other data. But the only point is that specific goal that we have is one of those INJs that are not in our data set. That's why we need more data about it. Because one of the students asked me later, are we going to use only the ratings of that specific users for prediction for that user? It is true, but we need the other data of the other movie and rating pairs as well. So since predicting that task is a little bit harder for an introduction course, we just stop at the formalization of recommender system, predictions, because there are tons of research, open research questions about it. But in order to use a linear model, we focus more we focus more on the credit card application, and that's what we're going to do today. All right, let's just. And also the other point is I've received many questions about the hypothesis. So hypothesis is just a set of formulas you're going to use that helps you to learn better. So using those formulas might involve having certain weights, but they're not weights itself. It's a bunch of formulas. One of them might work better, and that's going to be the candidate formula that you're going to use with your learning algorithm to make your learning model. So hope that clears things. So let's just recap a little bit. I've seen that in order to be unified with the other lecturers as well, so they have been using this type of notation, so I just wanted to bring this up so you are familiar as well. But in the exam, use whichever you're more comfortable with. I mean, notation is not important. So our data vector could be presented as a vector of x, like this, if you will, and that's that vector of x is within all the x's we have, and also is in the d dimension R space, so that d is the length of that vector. So you can define it this way as well, but both cases are the same. So this just shows that your x has d, so like 1, 2, up to d. And each of them could have some value. And also, as you know, your target function is unknown, and your target label is the one that you're going to predict. For instance, in the credit card application, is the one, so it has the space, and that's your output. For instance, in the case of credit card, it's either +1 or -1, and that's your Y label. So we can define it this way. And we use our training data, x1s, y1s, up to xn, yn's, to come up with, and to pick one of the hypothesis set and pair it with the learning algorithm. So given d, we output a function g that mimics sort of our f of x that is unknown. So to make prediction for a new input. And that input was not in our training data. Because if it was, we already had the label and the output for that, so we didn't need any prediction for that. So for a new input, we're going to use the available training data to pick up a hypothesis and pair it with the learning algorithm to come up with a new prediction. Yeah.
Is D just like pairs? Is D all D is pairs of existing X's and Y's?
Yeah. In the case of in your case, yes, D is is having the same length, but D is only your features dimension. So like you have D features. It could be 100 or 200 or 1. Not 1, but 3, 10, 100.
There's as many pairs as we have X and Y's. Like that can match together.
No. Your D is the feature vector length. So this is, if you want to have it in a CSV format, you're gonna see maybe databases or Excel. So this is your D, and N is this. So D is the number of the columns you have, and N is the number of rows. So N is your data set row number, and D is your feature number, which is in column normally. We're going to come back to it later, but just to have a formal definition, just know that, so the more observation you have, the more data set you have, the more history record we have from, for instance, the customers from bank, the more movie rating you have, so the longer your N would be, because you have x1 up to x and yn. But this one is a representation of that specific problem. Like for the bank, you have age, you have residency, the number of years in the residency, current debt, and other things. Okay?
And so correct in case what he meant by D was the capital D, the training case, not the small.
Yeah, I did. That was.
Oh, yeah. So are you talking about the capital D?
Yeah, what's a small D?
Not necessarily, because capital D contains the set of all training data, like this.
Yeah. I'm saying is that's pairs of inputs and existing inputs and outputs that we know of. I mean.
Yeah, they are the existing input and outputs that we know. That's right.
Okay.
They're historical records, right? All right, let's just come back to the one that I showed yesterday, last session. So in the case of credit card approval, so you're gonna have for the for our non-target function, you have the ideal credit approval function, which you don't know. For the training set, you have the historical record, as I mentioned right now. For the hypothesis set, you have a set of candidate formulas that you want to pick, and the one you picked is going to be your candidate one. And you're going to pair it with your learning algorithm, and these two are going to call together learning model, and then you're going to come up with the final hypothesis. So this G tries to mimic the behavior of your F. So I'll stop here for like 10 seconds if somebody wanted to note down. All right. So let's talk about hypothesis set a little bit more. I already mentioned it once. So this is basically one more reiteration. So I mentioned that hypothesis set is a set of candidate formulas, and it plays a vital role in a learning process and how well we can learn. We could choose another hypothesis from our hypothesis set, but if it wasn't the candidate one who was outperforming the other hypothesis, we wouldn't be having the best possible prediction. We could still do some prediction, but we have to always pick the best one, and we call it candidate from among those. All right. I mentioned also in a previous session that, for instance, in the case of neural network, the hypothesis said that we chose as the candidate one. All right. And then we started talking about Perceptron. So first of all, we talked about if our data points are linearly separable or not. So this is a case on the left side that your data set is separable. So let me show you one case that is not separable. So suppose that was your space of data with pluses and minuses. So you had pluses here and also here, and you had minuses here. So this case is representing a data set that is not linearly separable, because with no linear line, you can find a linear class separation between the pluses and minuses, unless you pick a nonlinear shape like this or a shape like that. There's no way with one line you can separate these two. But that case that I show you have a linearly separable data set actually. So and that's the starting point of your perceptron algorithm. So we want to make sure that we start from one random iteration, and then we pick one of those that were misclassified. So in this case, this one was misclassified, the green class, and we want to make sure that we nudge a little bit that red line, our classifier, to the point that all the pluses and minuses are in different domain. All right? And I mentioned briefly that this line, your red line, will change with the choice of your W's and the threshold in the case of credit card approval. Also, another properties for this line is this line could be middle lines. Like if you have a a space of data like that, you could have like so many other lines that would still do the job perfectly. Yeah.
To be clear, we're still talking about a credit card example.
Yeah. Yeah.
Are we saying that these are like this is we're looking at this in a 2D graph, so the pluses and minuses are all like points of y right there. Up.
That's right.
So the x and y would have to be two different variables when it comes to x inputs. Like one would be x1, the other one would be x2. Like what's like we're looking at a 2D plane right now.
Yeah, just think about pluses as in the case of credit card, it was +1, so it was approved. The case of output. And minus was -1, which was rejected.
No, right. But I'm saying like the x and y axes here must be two different. Like it must be two different properties of x inputs, right?
Are you talking about x and y here?
Yeah.
So, because here we had a binary classification that I'll explain next session. So you have two classes, which are binary. We're gonna have multi-class, prediction as well. So in that case, you have a three-dimensional space or even higher dimensional space.
Right. So I'm saying here in our just third example would just be so this would be representing two different aspects of x. If we had like we were saying, okay, based on the age and gender, we're gonna decide if we're gonna approve you or not. But like in reality, we're talking like 30 dimensions.
Right.
So we're looking at a simple level.
If like you were to predict on ImageNet class, which has 1,000 classes, yeah, that would be 1,000 dimensions. Yeah. There was another question, I guess. So very good. All right, now let's go to the perceptron learning algorithm, or PLA. So how are we going to learn through this perceptron that we described? Okay, go back to the credit card application. We mentioned that the hypothesis X, the hypothesis H that we chose, H of X, is a sign function of the summation of yi's, xi's minus the threshold that was the threshold of the approval of the credit card of the bank. And we formalize it this way. And we mentioned that if we change wi's and thresholds, it's going to define another hypothesis set. But that hypothesis is still another formula that we need to choose. So we change it to a vector space, and we define an artificial coordinate, which is called x1 for the x0 for the threshold. So if you start with that, the sign function threshold, and it was I1, Then if you assign this to an artificial coordinate, which we call here W0, and then also we call x0 is equal to 1, so you can formalize it this way. So it's going to change into the sign. You're going to have the summation of your yi xi, but instead your I starts from 0 with respect to the 1 and ends at b. This will cover also for your threshold. All right? Question?
So the hypothesis set, they're just functions that we can use to map inputs to outputs, right? Right. Yeah. How is like backprop? Isn't that more like an optimization method than a hypothesis?
So you use so yeah, I'll explain it in details when we reach neural network. But you can use backprop to read the learning algorithm, read a stochastic gradient descent or other things to optimize neural network. But backprop itself is a nonlinear function using different derivatives at each layer of the network. So yeah, it's in essence is a function. It's set of formulas. Just think about it. Yeah.
If we're setting W naught to be the threshold, should X naught be -1 then? Or are we saying W naught would be like an actual negative number?
Could you repeat the question? Could you repeat it?
We're good.
Are you good? Okay. Okay.
So I actually had the same question. You said W naught is equal to threshold?
What is it?
You set W naught to the threshold and you introduce X naught equal to 1. I think if X naught equal to 1, the threshold should be negative. Like
Where we mentioned x is not equal to 1?
it's on there.
Here? No, it says x0 is equal to 1.
Yeah, X0, okay, yeah, X0 is equal to 1.
Right.
And you say W0 is equal to threshold.
Yeah.
Shouldn't W0 be negative threshold?
But when you bring it back here, bring it back to the other formula. No, okay, I understood what you mean. Yeah, in essence, it could be minus at some point. Yeah, but in order to formalize it this way, right? Yeah, it could be in some cases. It depends on the threshold. Right. Yeah, I appreciate all these questions. Okay. So now we transform this to a vector space, and we transpose the vector of W. So now your W is a vector starting from this. That was your W vector, and you transpose it, and so this is your WT. So the first one would be your 0, W0, W1, and going to the end, WD. And your X is this now, 0, 1, to D. Okay? It's just another form of representing it in a vector form. Like that. All right. Now, let's see how PLA can help us to training step by step and converge to better point to classify it better. So we need this for our all x1, y1, x2, y2, and so on and so forth up to xn and yn. So the PLA starts from picking a misclassified point in our data space, just one of the classes that I showed like in 2 slides ago. So it's going to pick that misclassified point. So the misclassified point is represented by either +1 or -1 in our yn. So that means that +1 had to be -1, but is misclassified as +1. On the other case, when you have a misclassification of -1 in a binary space, so it should have been +1 and you misclassify to -1. So these two cases occur, right? So either of these two are a misclassified point. So At this point, the PLA algorithm starts to update the W, the weight of W, to change the slope of the line. And how it's going to do that is, so that's going to be your old W, and it's going to add it with yn, xn. I'll explain in a second how does this work and why we have the plus yn and xn. So it picks one misclassified point. It's going to update the W and assign a new W for that, and then loop over the remaining data in your space and see if other misclassified point still happens, or by changing the first one. So you had like this. You started from this, so that was the point that was misclassified. By updating weight, you push this line down, and let's have another minus here. You push this line down, and then you're going to have a new line here. This one was solved, but then now we have another problem here. Okay, so you have to iterate over this for all the data sets. I'll visualize it in the next slide as well. So let's talk about why you have to update it this way, plus yn and xn. So these are the two misclassified cases. The first case. So since we are talking about vector space, suppose you have two vectors, which are w and x. So if your x vector lies this way and your y vector lies this way below the 90 degrees, so the inner product of these two must be positive, right? Because they are in the same quarter. So since it wasn't, because the x and y was having more than 90 degrees in the vector space, so we found out this is a misclassified point. But the classification tells us that it was plus 1. It should have been minus 1, right? If we add to the y vector, yx is going to come back here to the green arrow, to the green vector. And now we have a right classification on that, right? And actually, because y is 1 here, so you're going to add y plus x. So you just add the x vector to the y to the w vector, and it's going to go back here. So now the classification is same plus 1, and these two are actually presenting that, right? So this is the case 1. On the other side, these two were representing a plus 1 classification for y, and y should have been plus 1, but it turned out it was minus 1. So if you add this, that's actually subtracting this from w. So the new one, the corrected weight, is going to be w plus yx. And now it's representing the correct the classification. Is it clear?
How does this guarantee the is not correct?
How does this guarantee?
That this point is not correct? Is it still being misclassified?
How does this guarantee? So it has been mathematically proved. You know, there was a proof for that that you don't have to know. But if you visualize it like this, there are only two cases in a binary classification of plus 1 and minus 1. Either they were this and they were classified as minus 1, or they were this and they were classified as plus 1, and these two are correct. Make it correct after that. So it's going to update the weight. All right. So now let's see the iterations of PLA. Yeah.
So if you only update it what is wrong, right?
Yeah.
And then this process would only fix the results for that point that got wrong.
Right.
But wouldn't it? If you continue this process, wouldn't it contradict with another point, like you
Yeah, absolutely.
fix this one, you mess up the other?
Yeah, that's exactly what I showed here. So it happens that PLA starts from a random misclassified point. It starts to go over a loop and iterate over all the misclassified points and start to locally update the weight for each of those. But doing that was, forcing the other points to be misclassified. And that's why you have to go over a loop. But eventually, it has been proved that if your data space is linearly separable, after a certain step, it's going to converge. Because if you, in a worst case, if you explore it exhaustively, you're going to find that line or one of those main lines that separate it perfectly. But it might be the 10th iteration, maybe in 11th iteration, you might go even worse than the first one, and then in million iteration, you come back to the optimal point. All right, so these are the 3 steps of the PLA. For one of the iterations of PLA, you start updating the weight, W, where X and Y was a misclassified training point, just like this. So you start picking a misclassified point like the green plus here, and you push over the red line towards, having this included in the green region. And after that iteration, you see that this one was fixed, but our -1 in blue is misclassified now. So on the next iteration, it has to pick that and then play with the line again in order to fix that. So, and then it's going to go on. So at iteration T1 up to Tn, which is the size of our ends, pick a misclassified point, and then run PLA on it. So the PLA was updating the weight for us. And that's it. So after some iterations, eventually you're gonna find the right classifier that can classify your linearly separable, space. All right, any questions from PLA? All right, now let's talk about. You were taking a photo? Your colleague, maybe? Okay, let's talk about the learning types in general. So mostly, so far, we've been talking about some supervised learning, and I implicitly mentioned what the definition of a supervised learning is. But now you can see that supervised learning is a type of learning that you've got labels or you've got outputs for your data set. So the outputs are either given to you or you have obtained the output yourself. For instance, in the case of ImageNet dataset that I described in the first session, so you're going to have millions of images with their label classified in 1,000 classes, like breeds of dogs, cats, cars, humans, or other things. So somebody would have, see the photos and then label them as like this one is the label class 42, and 42 represents one type of breed of dogs. So you have this for all of your data set, x1, y1 up to xn, yn. So when you apply your learning model, it's going to see if it was correctly classified or not, and based on that, it's going to correct it. So the way you update the weight in PLA, it was like this. In other SVM, might be another way, or in neural network, might be another type. So, and that's going to be a classic supervised learning. There are other types of learning problems. One of them is called unsupervised learning. So what if you didn't have your output of your data? What if you didn't have any labels? So you had a good example is like you have a bunch of coins, like fives, dimes, quarters, or some cents, 1 cent, and then so they are representing 4 types of coins, but you don't have any labels. Like you could only maybe touch them without looking at them, like with your eyes shut. Or suppose you are a vending machine that accepts coins, and it cannot take a photo from the coins, and you just have to detect what coins are getting inside the machine. So there are other techniques that you can use in order to find some or gain some information from that unlabeled data. And we're going to talk about it later when we start unsupervised learning. Techniques like clusterings or density estimation or other things. But definitely unsupervised learning are much more harder than supervised learning in general because you don't have any labels. You start the problem with little information. The third option, the third category of the learning types is called reinforcement learning. So it's not that bad of having lack of information, just like unsupervised. You have some outputs, but by having some outputs, you have some grades for those outputs. So think about those grades as rewards. So suppose a robot is hovering on Mars. Okay, so a reward could be getting not hit by a rock when it's like going forward. Like this is a robot. I don't know what to. This is a car, maybe. So this is our rover, and there's a rock here. So it has the option to go in either of these dimensions. Okay, suppose, and when it hit the rocks, it's gonna stop, and it has to turn some way around here. So it has to update its reward function that what choices does he have right now, left, right, up, and down, to maximize its reward function. And one of the reward functions could be like not to hit the wall or just not to fall down in a pitfall or any other thing. I mean, we don't have that much time to go for reinforcement learning, but just normally you see that mostly on gamings when you have multiple agents, when you play chess with a computer, or backgammon, or the example that I showed you in the first lecture, the AlphaGo team playing with the champion. So these are some of the examples for reinforcement learning. Let's just go through and have some more examples. So for the coins that I was mentioning, so if you represent it in a classified way and that you have labels for your coins, is as if you color them in different colors by their different type. So like this represents your 1 cent, this represents your 5 cents, or the other one is like quarters, the other one is your 10 cents. So you know the label, and when you predict and when you misclassify it, you can understand that, okay, I had a prediction error, so I have to correct it. The other example could be a medical diagnosis. So you have list of symptoms, and then your output Y would be, is the patient actually sick or not? Or does he have a specific disease or not, given that list of symptoms? This is another example for supervised learning. Question? Okay. Another famous supervised learning problem is handwritten digits. So your X vector represents some images of digits, like this, maybe. So that's your input. So suppose it's in pixel format. So when you have 1, so you can have pixel of the images and input that as some numbers, right? So these are the pixel of your image, and that was your 1. So given this input, your job would be to classify it, and you know the Y label is obviously having from 0 to number 9, which represent the class of digits you are inputting. So this is another interesting example that you can expand into other classes or other handwrittens as well. All right. But if you go unsupervised, it's as if I remove the colors from the coin here and represents a data just like this for you. So instead of having that, you're going to have this. So you see, it makes the problem a little bit harder because you don't know how to start with, checking if your predictor was doing correct or not. So there are other techniques that you can apply, like clustering, that we're going to mention later, and it's going to help you to identify them, I don't know, by their shape, maybe, by their mass, or other information. And though you don't know what they are, but you can tell something with some accuracy that, okay, this is one type, I don't know what type, but I can call it type 1. And that could be type 2, because I think that these are different in mass or shape or in weight. And I have 2 more types as well. It might be that these lines that I draw are not that perfect because, I couldn't do much better about it. But at least I know that there are some type. It's like as if you start listening. As another example, suppose you want to learn a new language, and suppose you want to go to Italy, and you start, taking some online classes or just listening to radio. So at first, you don't know anything about that language. You just hear something like ciao, tutto bene, or other stuff. But after a while, your brain gets to train a classifier which is very vague. But when you are outside Italy and somebody spoke Italian, although you don't know anything about it, but you think that, oh, this might be Italian, this resembles Italian. It's just like this. You can sort of classify the type, but you don't know what the type was. So this is an example of unsupervised learning that, this is just like a higher representation of your data that you have, but you don't know exactly what the data was. All right, and so let's go for an example for the third one, and that's going to be after this, the reinforcement learning. So I mentioned instead of input the correct output, you have some outputs with their grades. So as if you're playing backgammon game, and by each round of play, you gain some rewards. You can define your rewards is by winning certain internal games or eventually winning the whole game as well. And as you know, the world champion was a neural network as well, just like chess, just like AlphaGo, and other games as well. All right. Any questions for this session? Also, let me remind you that the first assignment was posted, so check workers, and I think the deadline is 13th of January. 30th?
Yeah.
All right. If there is no question, maybe we can wrap up this session, and I'll see you on Monday. Okay?
Is there a tutorial this week?
I think there was one. I think there was one on Wednesday, right? If you can attend it, yeah.